In our last lecture, we started the discussion on how to represent real numbers in computers. We are talking about scientific notations. Let us continue the discussion. First, let us recapitulate a bit to have the continuation. Suppose we have a number, a decimal number. Zero point 0.000567446. Now, this number, to write it this way is a little bit awkward, and so what we do is this, that we generally write it in the scientific notation 0.56746 into 10 to the power minus 4. Now you see, if there are more zeros, then this number, this way representation of the number is definitely much more convenient. Okay. Now, if we have a decimal computer, in that case, how will we represent this number in the computer? We'll have to keep a position for the sign, which is plus here. Okay. Say this is our position for the sign. Then we should keep a position for what we call an exponent. Okay. Say this is exponent, which is, this is plus, this is minus 4 here, and few positions for the what we call is a mantissa or significant, say 5, 6, 7, 4, 6. We call this exponent, and we call this mantissa, or sometimes we call this significant. Decimal point is assumed to be here, but it's not represented. Now, once more, in that positional number system, the weights of the different numbers are like this. Say, for example, 0.56746. The weightage of this number is 10 to the power minus 1. This number is 10 to the power minus 2. Weightage of this number is 10 to the power minus 3. This is 10 to the power minus 4. And this is 10 to the power minus 5, and so on. Now, say we do not have, say, 5 positions to represent the mantissa in our computer. In that case, what we'll have to do is that we'll have to discard this decimal digit, and if we discard this decimal digit, we will have to round off the previous digit to, say, 5 here, since 6 is greater than 5 in this position. Now, we call this a scientific notation. We also call this a floating point representation. A floating point representation. We call this a floating point representation because the decimal point is slided as per the convenience to a specific position. Okay, that is why we call this floating point. Say, similarly, if we take a number which is a negative number, say minus 5670242.9836. If we have, this is the positions for accommodation of the real number as a floating point number, naturally we will have to represent this as minus then the decimal point is shifted from here to here by position 1, 2, 3, 4, 5, 6, 7. Therefore, minus plus 7, and then we can represent only 4 digits, which is 5, 6, 7, 0. All the digits from here have to be truncated out. Therefore, this is our sign position, this is our exponent, and this is what we call our mantissa or significand. Okay. Now, similarly, since our computer deal with only with binaries, we can have a floating point representation of the real numbers in binary. Let's take an example. Say, take this number plus 0.1011. Now, this is also, we take this as a positional number system. The weight of this number is 2 to the power minus 1. The weight of this bit is 2 to the power minus 2. Weight of this bit is 2 to the power minus 3, and weight of this is 2 to the power minus 4. Since our radix is 2, therefore the powers after the binary dot is this. And this number will represent once more this way. So we have a position for the sign, we have a position for its exponent, okay, and we have a position for the significand or the mantissa. The mantissa, the sign here is plus, therefore let us represent it the plus by 0 as usual. The exponent here is 2 to the power 0, that means it is 2 into 2 to the power 0, that's the number we have taken. Therefore, exponent is say 0, 0, and the mantissa is 1, 0, 1, 1. We assume a binary dot here, which we do not represent. Okay. Now let's see, take the number, say 110.0011. This in our floating point representation will be 0.1100. So 4 bits we can represent only in our computer. This is our mantissa. The exponent will be 2 to the power 3, 1, 2, 3, therefore it will be 0, 1, 1, and sign is positive, therefore we can represent the sign to be as 1, okay. This is the sign. Therefore, in this representation we have, the sign is positive, say let's take this a negative number, okay. Therefore, the sign is negative here, okay. Therefore, we have here representation as 1. The mantissa is 1100 and the exponent is 0, 1, 1. That is our floating point representation of this number. Similarly, we can have a number, say for example, if we have a number say 0.000101, then the floating point representation of this number will be, say this is a positive number, therefore sign is 0. The exponent is, it should be minus 3, okay, therefore say 1, 1, 1 in sign magnitude representation, minus, and the mantissa will be say 1, 0, 1, 0. Okay, this is the mantissa, this is the exponent, and this is the sign. Now, this I have represented this minus 3 in the sign magnitude form. Naturally, we can represent it in the 2's complement form also. Exactly how it is represented, we'll come to in our next few seconds. Okay. Now, if we do it this way, say, then we can represent any number, a floating point number. The property, let's see the property of the floating point number. Now, the floating point number essentially, say, for example, when you are representing it as a decimal, you see, when you say that we are representing as a floating point representation, what essentially we are trying to do is that the most significant digit has to be a non-zero. That means we are sliding the decimal point to a position where the most significant digit is a non-zero one. Say it is here, it's a non-zero, right? For example, similarly, in the case of that negate this number, we have slided the decimal point here, but the most significant digit after the decimal point is a non-zero. Similarly, when you are representing a binary number, you see here, we are shifting the binary point here so that the most significant bit after the binary dot is a non-zero, which is a 1. Okay. Similarly, here also the most significant bit is a non-zero, which is a 1. If we take this representation, and if we have 32 bit to represent it, then we can represent a number, a real number, in the format that has been shown here. Okay, we keep the sign bit, the most significant bit, as a sign bit of that entire number, whether the number is positive or negative. We keep that exponent, say 8 bits exponent we keep. If we keep that 8-bit exponent, and if we can represent in the 2's complement form an exponent 2 to the power minus 128 2 plus 127, and here we can keep 23 bits for the mantissa, starting from the 0th bit to 22nd bit. Okay, this is the mantissa. Now, this is if we represent the exponent in 2's complement form, we can represent minus 128 to 127, right? But IEEE 754 standard, where IEEE is the Institute of Electronics and Electrical Engineers, they set up standards for many things. For this representation also, they have set up a standard, that is floating point representation. They take a biased 127, which means that if we want to represent minus 1, then 127 will be added to it, so which means that minus 1 will be represented as 1 plus 126, and its representation naturally will be this. Similarly, plus 1 will be represented as plus 1 biased 127, which will be 128 and will be represented 8 bits this way. Now, the reason for such a representation is this: the sign bit is brought in the first position so that immediately the sign of the number can be known. Okay, so that a positive number can be treated to be immediately higher than a negative number, and ordering can be placed. Similarly, if we take biased 127, in that case, by seeing that exponent only, then ordering can be done, which means that a number with higher exponent having the same sign, okay, it's a positive sign, will be higher than the number with a positive sign with the lower exponent. That way, that exponent has been brought after that, and only after that the significand has been placed. Now, if you try to look into somewhat more details of the floating point number, okay, that what number we can represent, you can see that if we have a finite representation of a real number by means of a floating point number this way, where we put a binary point, assumed to be a binary point here, only 8-bit exponent we have, and we have a significand of 23 bits, then the number set that we can represent is this. that say this is the real number line and continuum is going minus infinity this side and the plus infinity on this side. We have a 0, and that 0 is both exponent 0 and the mantissa 0. Then the first number that you can represent is 0.5 into 2 to the power minus 128. I have assumed to be in 2's complement representation for the exponent. Okay, first number that we can have is that 0.5 into 2 to the power minus 128. How does it come? Let us see. In the first number will be that mantissa will be 0.1 here, since this has to be a non-zero bit. Okay. After that, all the bits will be zeros, which gives a value of decimal 0.5. Exponent is the minimum. That means an 8-bit minimum exponent is minimum value is minus 128. Therefore, this value is 0.5 into 2 to the power minus 128. That is the minimum value that you can represent in the case of a floating point representation. Positive side. Similarly, the highest number that you can represent is that mantissa is 0.1 and all ones, that means all 23 bits ones, and the exponent is the maximum value, which is 127, and the mantissa's this value in decimal is 1 minus 2 to the power minus 23, okay, when all ones are there in 23 positions. Therefore, this is the maximum number, positive number that we can represent. Beyond that, there will be a positive overflow, and below that, there will be a positive underflow. Similarly, since we can have both positive and negative number with the sign bit only, the sign bit is 0 for positive and the sign bit is 1 for negative, we can have minus 0.5 into 2 to the power minus 128 is a minimum the number that we can represent here, and minus 1 minus 2 to the power minus 23 into 2 to the power 127 is the max, the least negative number that we can represent here. There will be negative overflow beyond this and a negative underflow here. No numbers beyond this can be represented, no numbers beyond these can be represented, and no number can be represented around here and around here. Another important point is that when we have such a finite representation, even all numbers within the range cannot be represented. Okay. Let us take an example and show that what can be the pitfalls of the floating point numbers. Because of the finite representation, the continuum from here to here even cannot be represented. Okay. See, we have taken as an example a floating point representation where this is a sign bit, 3 bit has been kept for exponent 1, 2 and 3, and 3 bits have been kept for mantissa, right? You see that 3-bit mantissa, if the most significant bit has to be 1, in that case these are only 4 patterns that we can represent for the mantissa. The corresponding decimal values have been kept here. Okay, the decimal values is 0.5, 0.625, 0.750, 0.875. These are the only 4 representation we can have, right? And here you see that 2's complement, if we take that exponent to be in the 2's complement form, then this will be the numbers that we can represent. Okay, that minus 4 is 100, minus 3 is 101, and so on. 2's complement we can represent here. Now, if we have to represent in the biased form, then 0, 1, 1 has to be added, and we can represent the biased exponent this way. This will be minus 4, minus 3, and so on to plus 3. Now, in terms of IEEE representation, this number is not used. Okay, therefore we have from 0, 0, 0 to 110. You see, that's a ordered set in terms of if we assume it to be unsigned number. Okay. Now, in this representation, you see that these are the only numbers on positive side I have taken only. These are the only numbers that we can represent. Say we can, this is a 0 here, okay. Then 2 to the power minus 4, okay, that is the exponent that we have, 2 to the power minus 4, and for this exponent we can have 1, 2, 3, 4, only 4 numbers that we can represent. So for example, let us take 2 to the power 0. The numbers that we can represent is 100, 0.100, 0.101, 0.110 and 0.111, each having an exponent of 2 to the power 0. Therefore, only these 4 numbers 1, 2, 3, 4 that can be represented for 2 to the power 0. So is for 2 to the power minus 4, 2 to the power minus 3, 2 to the power minus 2 and so on. Therefore, you see on the positive side, how many numbers we can represent is, say 4 mantissa representation for each of these, assuming that we are taking 2's complement representation, each of these 8 possible combinations. Therefore, only 32 positions I can represent. And you see that from here to here, this equal spacing. Immediately, if you go from 2 to the power 0 to 2 to the power 1, the spacing between 2 numbers immediately increases. Okay. For example, the spacing is this much here, then spacing is double this much here. Okay. Now, you can immediately see that as I was talking of, that numbers that we can represent falls within this range. In this range also, we can represent only a finite points. Okay, that means only a finite set of real numbers within this point, and immediately that creates a good amount of error in representation. Two things immediately happens. You see that because of the finite representation, one number in a decimal system cannot be exactly represented as a number in the floating point representation and vice versa. Not only that, you will have problem of representation even of X number when you are trying to represent it. Okay, so for example, if you take say decimal 0.7, right, you try to represent it as a 8-bit number over here, okay, with this exponent, and you'll immediately find, I mean, with 8-bit exponent and 23-bit mantissa, you'll immediately find it's very difficult to represent exactly 0.7. Now, let us see what are the ranges that can be represented, that can be achieved with such representation. Okay, if we assume that we have a 32-bit number, as is the situation here, we have a 32-bit number, and if we use the number of exponent bits to be 8, okay, either in say 2's complement form, or you can represent in biased 127 form in that IEEE 754 standard, then the equivalent decimal exponent that you can represent is 10 to the power plus 38 to 10 to the power minus 38. If the number of mantissa bits is 23 here, then equivalent significant decimal digits that you can represent is 8. Now, if we go, this is a float, okay, in C. If we go for a double, okay, where we use 64 bits, then you see that immediately the number of exponent bits we can make to be 11. In that case, the equivalent decimal exponent that we can represent is 10 to the power plus 308 to 10 to the power minus 308, and the number of mantissa bits, if we use at 52, then equivalent significant decimal digits that you can represent is 15. Okay. Now, let us talk about some more problems regarding that that floating point representation of a decimal number. Suppose that you take one number, say 100, okay, and another number 0.101 into 2 to the power 0, and you try to add. Let us see what happens. Say 0.101, okay, and we are adding 0.100, 0.100, 2 to the power 0, 2 to the power 0. You see, then if we add them, what we get is 1, 0, 0 and 1, right? Which essentially means that if we want to represent it, the decimal or the binary point should move over to here, and we have immediately a number which is 2 to the power 0.100 into 2 to the power 1, right? Which means that the number, by adding this and this, we have come to a point between this number and this number, these two representable numbers, okay? These two representable numbers means that somewhere here we have been mapped into. Naturally, this number cannot be represented in our this machine where we have kept only 3 bits, okay, for mantissa. Therefore, this number has to be rounded off, right? And we can round off this number by, say, discarding this bit and come over to here as 100, okay, 0.100 into 2 to the power 1. Now, how this rounding off will be done, okay, that we will be discussing after some time. And another pitfall comes this way. Say, for example, if we have a number like, say, 0.101, okay, and say 0.1010 into, say, 2 to the power 010. Another number you have 0.10, say 11 into 2 to the power 001. Say both of them are positive numbers, and if we want to add them, you see what we'll have to do. We'll have to first align the mantissa, okay, by either increasing or decreasing the exponent. Here, naturally, the lower exponent has to be changed, and the lower exponent has to be changed, and the mantissa of the lower number has to be accordingly aligned. For example, this we'll have to do this way, that 0.1010, 2 to the power 010, and 0.0101, this one will flow out into 2 to the power 010, and then only we will be able to add, giving a figure of 1, 1, 1 and 1 into 2 to the power 010, right? Which means that whenever we are trying to do that arithmetic operation, say like this, we will have to first align the mantissa depending upon the exponent. Naturally, the lower exponent has to be raised to the higher exponent same value. Accordingly, the mantissa has to be shifted to the right, and only then the addition can take place. Now, this addition, okay, this is the sign bit, this is also plus, this is plus, and therefore I am simply adding over to here. This is represented by 0 plus 0 by plus, okay. Now, this is the way that addition has to be done. Okay. Similarly, for addition and subtraction, the same procedure has to be followed, and we can represent the basic steps of addition and subtraction this way, that we check for zeros. Okay. Naturally, that floating point numbers we are trying to add or subtract, we will have to check for 0 first. If you find that one of them is 0, then the other turns out to be a result. Otherwise, we align the mantissas, then add and subtract the mantissas, normalize the result, and then we should round off the result. Okay. Let us see, taking this, what can be an adder subtractor unit for a floating point number operation. Okay. So this is one number, and this is another number. this is a sign, this is the exponent, and this is the mantissa of the first number. So for the second number. Now here, that what is done is that we have a small ALU here, which first compares the exponent of this number and this number, okay, and that exponent difference is found out. That now controls, puts as input to this control element. Now that control element as an input to this, we call this a multiplexer. The multiplexer is a 2-to-1 multiplexer. That means depending upon this control signal, one of the input will come as an output, right? Now this multiplexer does that the larger exponent comes out as an output here and comes to this register, the exponent register. Now this control also controls this multiplexer and this multiplexer, right? So that here comes the mantissa of the larger exponent number, and here comes the mantissa of the lower exponent number, okay? You see, we'll have to align the mantissas depending upon the difference of the exponents. So the number smaller exponent comes over to here and it is shifted right, okay, to bring it to the same exponent as the number with the larger exponent. Then that arithmetic addition, subtraction are done, okay. Now here you see that we have essentially, as we have represented the numbers in a sign magnitude form, okay, say this is our sign bit, this is exponent, okay. We can assume that it is either, as I said, that is in 2's complement form, or more so, let us assume that it is in the biased 127 form, because that IEEE 754 standard is more or less honored by most of the computer manufacturers, okay, and this is a mantissa form, right. Therefore, here what comes is that when these two numbers comes, the two numbers comes with the mantissas as well as their sign bits that are coming over into as the input of the ALU, and ALU then does the actual operation depending upon the magnitude and the sign of the two operands and the operation that is involved in it. The actual operation is performed, and at this point the discussions that we made in our previous lecture for adding, subtracting with sign magnitude representation or with unsigned numbers are relevant here, okay. That ALU will do this operation accordingly, okay, as the representation is there and these magnitudes of the numbers and the sign of the numbers and the operation that is involved. Then the result comes into this register. The sign is sent straight over to here. The mantissa may have to be aligned, okay, depending upon the result by incrementing or decrementing that exponent, and after the result comes out of this, it is come to the rounding circuitry to the rounding. Let us first see that what mantissa alignment that maybe have to be done, okay, normalization may have to be done. Say we have a number, as I said, that's say 0.1010, and another number say 0.1100. In that case, if we add, then we have so 0, 1, 1, 0, and 1 comes here, and we'll have to shift right to get this number in the normalized form, and that is this circuit does. That means it shifts to the right and increments the exponent. Say, let us take the another what's the 0.1101 and say 0.1011, right, and we are subtracting. In that case, it will be 0, it will be 1, right, this will be 0 and this will be 0, and we get a 0 over to here, right. In that case, naturally the entire mantissa has to be shifted left to normalize it so that the binary point comes over to here, okay. That is why here is that is that normalization is done, right? And the rounding is done this way. So for example, you have to shift out, right? For example, instead of this, had this been 0.1010 and say 0.1101, and if you're adding, right, in that case this is 1 1 1 0 and 1, and the binary dot is here, which has to be shifted to this place, and to represent in the 4-bit representation, we'll have to naturally discard this 1 bit. Okay. Now, when we discard this 1 bit, then the previous bit has to be rounded so that then it is represented, the number can be represented to the nearest form. The rules for the rounding of may be many, but one rule can be applicable, may be made applicable. That is, say for example, if the discarded pattern from here to here is 1, first bit is 1, and then there is at least some 1 bit here, in that case simply increment the previous bit. Okay. If this bit is 0, irrespective of what bit you have, okay, then simply discard these bits and you don't have to do anything to the previous bit. But if the first bit of the discarded bit pattern is 1 and you have all zeros over to here, then change this bit, that means change this bit pattern to an even number. That means if it is 1, you increment it to 0, okay, or if it is 0, you keep it as such. Okay, that can be the rounding of rules. Okay, this is a simple rule which can be applied for rounding here. Now, so this can be a floating point adder subtractor unit, okay, the hardware unit where we have shown the logic. Now, how much the bit pattern has to be shifted, that naturally depends upon the result of this ALU, and therefore the result is fed to the control, which then determines the normalization that has to be done by shifting how much into in which direction, and that also controls the rounding that has to be done. Okay, that is for addition and subtraction. Now, similar will be the situation if we go for multiplication. Okay, by similar I say that for multiplications we'll have to have naturally a similar unit. Okay, say multiplication we are doing of two numbers, say check for zeros of the two numbers and take action if zeros. That means any one of them is 0, then we'll have to declare the result to be 0. Otherwise, we'll have to add the exponents. For example, when we multiply two numbers, like say for example, if we take the situation of a decimal number, say 0.52 into 10 to the power 3 and say 0.36 into 10 to the power 2, then if we want to multiply them, we have to do addition here, 3 plus 2, and these two mantissa are to be multiplied. Okay, this is what has been done here, that the simple algorithm will be that check for zeros and take action if zeros. That means assume that if one of them is 0, then the result is 0, then add exponents, multiply the mantissas, normalize the result and round up the result. These are the basic steps that we'll have to do for multiplication of two floating point numbers. Okay. Now, similarly, if we have to divide the two numbers, okay, then once more you'll have to check for zeros and take action if zeros. For example, if the numerator of the division is 0, then declare the result to be 0. If the denominator is 0, okay, right, then you'll have to declare the result to be infinity, okay, and you can stop the algorithm over here. Otherwise, you'll have to subtract that exponents, divide the mantisas, normalize the result once more, and round up the result. Okay, therefore, I have just shown the basic steps that is involved in the multiplication as well as in the case of a division. The detailed algorithm can be worked out, okay, and naturally the corresponding hardware units can be constructed. Okay. Now let us see what can be the errors of your operations. Okay. Now errors of your operations can be this, right? Let us see that what can be the errors of that representation. We have taken, say, the representation here, and we have taken the representation of here. Okay, we say that there can be error in that overflow here, with that positive underflow here, negative underflow here, okay, and negative overflow here. Okay, now to go into the details of it, you see, basically we can have an exponent overflow, right? We can have an exponent underflow, we can have a mantissa overflow, and we can have a mantissa underflow, right? Now, you see that exponent overflows essentially will come over to here and will come over to here, okay? In the case of a exponent underflow, will come here or will come here. Now, the mantissa overflow can lead naturally to exponent overflow, and mantissa underflow can lead to a exponent underflow, because in that case shifting is involved for normalization. Therefore, these are the errors that can take place in the case of the floating point operations and representation, and one has to take care about these errors. Now, one important thing that I should say, that when I say that, say, we have come back to the number representation, then when I say that this number is 1 minus 2 to the power minus 23, because that first significant bit of the mantissa has to be 1, that is why the maximum number is this and the minimum number is this, okay, on the positive side. So the negative side also the corresponding numbers. Now, since we know that the most significant bit, okay, after the binary point has to be 1, we may not represent it here. In that case, we can have essentially a number, we can go up to 24 bits, so to say, and we can have a number that is represented up to 1 minus 2 to the power minus 24, okay, on the positive side. So also in 1 minus 2 to the power minus 24 on the negative side, since this bit we know that always will be 1 and need not be represented. Therefore, in our representation, all the 23 bits that we have, okay, 0 to 23 bits, okay, can be essentially used for as if we have 24 bits over here, okay. This is one thing that I should explain. Another is that here when I represented this number as, represented the floating point numbers in terms of a 3-bit mantissa, okay, and a 3-bit exponent, you see that I have only shown the positive side of this number representation up to a certain point. Similarly, the negative side of the number representation will be the mirror image of the positive side, okay, right? And with this, I would like to stop my lecture on the floating point representation and the arithmetic involved in the floating point representation. You can see I could just give a glimpse of the entire representation and the arithmetic operation that is involved over here. you should take few examples on your own to make your ideas clear, and so that you exactly know what is the pitfall of representation in floating point number systems and what are the pitfalls when you do arithmetic with floating point number representation.